Thank you very much, first of all, for inviting me to be the keynote at this Sumo user conference meeting or user meeting. Like you said, I've been here a few times. I've been, when it was actually held in person in Berlin, I was there a few times, and every time I enjoyed it, and I felt very honored and very happy to be asked to do the keynote presentation. So as you also mentioned, this is me. I have the new chair of bicycle traffic. We've dropped the planning part of it off the name because I'm not a transport planner. I'm finding out more and more. I'm a precarious technical or traffic engineering person. And as you also mentioned, it's one of the 7 professorships for bicycle traffic that is funded by the Federal Ministry of Digital and Traffic. So it's really great that the government is putting some money into research and education in bicycle traffic. And it's great also that the University of Wuppertal applied and created such a nice professorship that has so much to do with modeling and simulation. And that is within the Fachzentrum for Traffic. We didn't translate yet, but we're working on an English translation, but we work all 7 professors on different transport related topics. So what do I do? Modeling and simulation are the things I love the most. That's what I did at my time in Munich. And I really like the challenge of trying to simulate and model bicycle traffic in particular. Data collection and analysis, as smart as possible. So video data analysis to get trajectories in automated processes, finding different ways to count bicycles, to differentiate between e-bikes and regular bikes, these type of things. Also, we're trying to bring forward at the chair. And one big topic is the education of future cycling experts. So we need people who are going to be able to make the cycling cities of tomorrow. So that's me. And luckily, I have a team with me now. I spent the last year building up this team. I won't go through them all, but we have a nice mix of people. We have an electrical engineer with us, a mechanical engineer, some transport people, some people with a more planning or sociology background. And we're all looking at bicycle traffic from a little bit of a different perspective with, of course, a lot our focus because of me on modeling and simulation. Okay, so first I wanted to start my presentation telling you a little bit about the cities that have shaped me as a traffic scientist, shaped me as a person. And this is where everything started. This is my home city of Calgary in Canada. I don't know if you can see my cursor or my mouse on here, but this is where, about right here, was where my house was when I was growing up. And I don't know if some of you in the audience have been to Calgary before. It's a city on the west side of Canada, about 1,000 kilometers from the ocean, right near the Rocky Mountains. And this picture that you see here, these big roads are really, they're representative of the traffic system that they have in Calgary. So you drive places with your car. And as you can see also in this picture, your car is normally a bigger car. It's not a small one that you see here. It's changed a bit since I've been in Germany. Active mobility has come a long way. There's some bicycle lanes, some people actually ride, although you have to say it can be very cold there. It's pretty hilly, and well, the distances are really big. It's a wide North American city where everything is far away from each other, but it has improved. And this is where I studied civil engineering with a focus on transportation engineering. And what I learned there is how to build highways like these ones inside of cities and outside of cities. And I didn't really question it too much because that is what I was born and raised with and what I had experienced the whole time until I moved to this city. This is Stuttgart in Baden-Württemberg, and this is where I did an exchange. And people in Germany laugh when I say it, but this for me was the first exposure that I had to a really multimodal transport network. I could walk places, and there was a really good tram and U-Bahn system, and even I could ride my bike and feel comfortable on the roads. It was some sort of an eye-opener that I thought, holy, there are different ways to move than just to take my car and park in a parking lot somewhere and go inside. So this was really new and exciting for me. And I decided I wanted to try to learn more about it. And that took me to my third city, which is Munich, like Michael already mentioned to us. And Munich took me even further in this direction, especially with bicycle traffic. people complain like they always do, but the network here is pretty good and it's getting better all the time. And it is possible, as far as I experienced it, to ride your bike everywhere if you want to. And the weather is pretty good. It's pretty flat, and it's a very nice city. And I had a chance there to study transportation, not just cars, but a whole mix of things. And then I planned on going home back to Canada and try to implement some of this stuff. But yeah, life had other plans, and I stayed there and did my PhD with a professor who realized relatively early that bicycle traffic is going to be pretty important. Okay, and this is where I am now. This is Wuppertal. It maybe is not as well known to some of you. It's a city in Western Germany, which is underrated. I've learned it's a really nice city and has some very good aspects, but for bicycling, it's difficult. It's really hilly. It's really tight. Like the streets are really narrow and there's not a lot of space for bicycling infrastructure. And even if there was, it's really hard to get up the hill. I mean, every day I do take my bike, but I barely make it up the hill back to my home before I'm really almost 100% out of breath. But there is a will to move forward in this city. That's really interesting and encouraging for me. Okay, but now the question that we all have to pose ourselves. I mean, these are the cities that I've experienced so far. These are the cities of my past and present, but how do we want our cities of the future to look? What do we want? Do we want to have this general map of a North American city where you can see here our main road users that we're serving are the cars, streets everywhere that are wide and easy to drive on, not a lot of space for other stuff, not very nice for pedestrians and bicyclists. This is a vision that many people, including myself, I have to admit, have, that one day somebody is just going to come, or some people are going to come and make all these cars, or at least some of the cars, disappear. They're just going to evaporate and we're going to suddenly have more space that we can use for other things. Of course, in this vision, there's still cars when we need them for longer trips, or maybe if you need to carry a lot of things. But the ones that are used to travel 4 or 5 kilometers to the kindergarten and back, they maybe just evaporate like that. And we suddenly have space for this utopia, or this utopia that I see and hear about in the bicycle traffic circles, where we have more space for humans. We have more space for kids and bicyclists and people to sit and eat. I think I didn't realize before I had kids how annoying a road is, even if only a few cars are going there a day, because you always have to be careful. Like, oh, my kid, please don't go close to the street. It could be that a car is coming and you could get run over. So you have to watch all the time. And if there's just no cars or fewer cars, or they're only in certain spots, then this constantly being on guard disappears and you can maybe enjoy the urban space a little bit more. So this is one vision, but there's many visions, of course. The world is full of different people, and these different people all have a different idea about what the city of tomorrow should look like, or maybe it should just look the same. And this is one reason, of course, why things stay the same for a while, but this is the vision I want to stick with today. Okay, in Germany, we have this term Verkehrswende. And I put this here in German because I don't know, maybe somebody else can help me if there's a good English translation. I tried and I came with transportation turnaround. Maybe we can talk about it after if someone has discovered a better term for it. But what this transportation turnaround is a fundamental transformation of the transportation system. So things, how we move, how we meet our mobility needs will be completely different, or very different than how it is today. And this is especially in terms of ecological objectives. So we want a system that meets our needs, but has less impact on the environment, less CO2, less noise, less fatalities, something that is gonna be friendlier for the world and for humankind. So this transportation turnaround is the word I will use today in my presentation, but maybe there's another one. Okay, so what are the building blocks of this turnaround? First and most important is to reduce the trips that we need to take. And we all saw this and are probably still seeing it with the Corona pandemic. We could work from home. Maybe you had a meeting with somebody who was somewhere else. They were in Berlin, or they were somewhere far away. Before Corona, you might have flown there or taken a train and gone there to have the meeting. And now it seems more normal and more realistic that you just don't do that. You just stay home. You can be perfectly on time, like everyone now is with Corona, or maybe 1 minute late, but not any more than that, and do the same work, but with less traveling. So this is one example of reducing our number of trips that we take. Once we have our trips, they're necessary to make. Everybody knows the push and pull to shift the modal use. We want everyone, or lots of people, as many as possible, to leave their cars and go to something that has a little bit smaller of an environmental footprint. This is a really old picture, but it still shows exactly what we want to do. Maybe it's a bus, maybe it's a bicycle, maybe it's just using their feet, or using a new e-vehicle, mini vehicle, micro vehicle, but to a mode or option that has a little bit less of an ecological impact. And then the third building block that we have here is improving. And improving means the system that we have today. Let's make it more efficient, that people don't have to stop and start and let out or make their tires rub against the pavement and put particulate matter in our environment. Let's stop that. Let's make the flow better. Let's make things more comfortable. For cyclists, for example, that they maybe don't need to stop at red lights or have a little bit wider of an infrastructure. Or we have systems that help us detect if a road user is there, if a pedestrian's there, not to hit them. Or maybe there's a system that you can not steer on the highway. Things like this improve the system, but they don't fundamentally change it. And of course, with microscopic traffic simulation, we're oftentimes exactly on this third block, this improve the system, test things that we want to have that make the system better. So I looked at the Sumo website to find out what people are doing with Sumo, not just me who tries to do bicycle stuff, but what are all the rest of the people who use Sumo doing? This picture is actually from my dissertation, so that's exactly what I did. But traffic signals is a big one. How can we make traffic signals work in a much, much better way than they currently do now? Routing, how can we suggest routes that are good for the whole city or maybe just good for the individual people? Less emissions, better travel times, more comfort. Human in the loop simulators. So we had a bicycle simulator at TUM, and I'm building one now in Wuppertal, and we will definitely use Sumo to put the traffic into that simulator. Vehicle communication. So vehicles communicating with vehicles or infrastructure. How can these systems work? What can they be used for? How can they improve the system that we have? Autonomous vehicles, of course, a big one. How are these going to work and what effect are they going to have on our mobility system of tomorrow? Parking, which is the antithesis of bicycle traffic. This is what I'm realizing more and more, but of course you can carry out bicycle or the parking traffic studies, I guess. With Sumo, I never tried it, but I learned on the website that you can do it. And traffic safety. Traffic safety is difficult with simulations since they are basically accident-free softwares, but of course you can get an idea, deceleration, what are they doing? Could there be some problems with traffic safety? But all of these things, of course, get the improve stamp on them. This is not changing our system, except maybe autonomous vehicles, but definitely making it better. So what I want to talk about first is if we just shift our focus for a minute away from this improve and to this push and pull or modal shift topic. And what I want to do first is just make a little argument for bicycles. I have a bicycle professorship and I am convinced that this is a mode that can bring a lot. And first, I just want to convince you all that maybe this modal shift is something that we need to really go for in the future. So I brought some numbers with you. First, the person kilometers traveled by bicycles per million per day in Germany. And you can see, which is really nice, that it's going up and up and up since 2008, which is when I got to Stuttgart, to now, or 2017. There's been a big increase, and this increase is continuing to increase. Mostly in big cities, mostly in Berlin and Munich and Hamburg, but also in smaller cities and sometimes on the countryside, not as much. But big cities, a lot of people are shifting towards the bicycle. And let's put some numbers behind what kind of improvement this can mean. The the Federal Ministry or Amt for Environment says that we can save 139 grams of CO2 equivalents for each one of these person kilometers that are traveled by bicycle instead of a passenger car that has an average occupancy of 1.2 or whatever that is. This is really hard to get a number for the cost benefit gained of cycling. The embassy in Denmark tried to get everything put together. So money that's saved from the healthcare system, that we have people who are more active and so have less problems with their heart or different diseases that come from being inactive. What can we save on infrastructure? Building a bicycle lane, of course, doesn't cost as much as building a whole street or something for motorized vehicles. What about the noise and the pollution and all these things that cars let out into the environment, but bicycles don't? They tried to gather all these things together and put numbers behind them, which of course is not an easy task and has a lot of presumptions behind it, but they did it and came with €1.34 per kilometer cycled compared to a motor vehicle trip. Okay, so let's just look what this is for 2017. If we calculate it out, we get 5.6 million tons of CO2 equivalent saved and 54.8 billion euros. So this is an opportunity that we have to really change something, which is why I like this picture so much. It was right before the World Climate Conference in Glasgow. This came up. This machine fights climate change. And of course, there are lots of other machines that fight climate change, but they are often much more complicated machines. Okay, so let's continue. I will stop plugging too much for the bicycle, although I have a difficult time doing that. Who do we have on our roads? Of course, we have motor vehicles. We have a lot of them. They have many different shapes. They have many different sizes. They have many different uses. They have different emissions. They have different acceleration and deceleration profiles. But we can put them all together under the category of vehicle. What we also hopefully have is pedestrians. So we have people who are walking around in our urban environment. These are some nicely simulated ones. And we may or may not have some cyclists. We may or may not have some cyclists of different shapes and sizes and abilities and motors that drive them, or people who ride them. And we have public transport in also different shapes and sizes. We have buses and trams and U-Bahns and S-Bahns, depending, of course, of which city you're in. And we want to bring all of these road users into a simulation environment. Going into the future, if we continue to simulate, which was often done in the past, urban areas, and neglect the pedestrians, and we don't include the cyclists because it's not easy to model them, or it's not good, and we make traffic lights, and they're going to work great for motorized traffic, but we just neglected the other road users that are there for that time. My hope, when there's more and more active mobility users, that these simulations are going to be less and less worthful. Anyways, so what are the differences? What do we need to look at when we're thinking about how do all these different road users behave in terms of what I need to simulate? So I picked 5 different categories of characteristics and looked at motorized traffic. Motorized traffic travels in one direction along a road. Normally, sometimes they go in the wrong way, but that would be bad, as is contact. We don't want any vehicles to touch any other vehicles, or that's an accident and can have very bad consequences. Any interactions are really regulated by traffic laws. Who has the right of way at an intersection, what speed you can drive, what you need to do at a traffic light. These things are all told to you by, or you learn them when you learn how to drive, and something that's not is maybe regulated then by cultural regulations, but most of it's traffic laws. And for that reason too, the speed is pretty uniform. People are traveling at the speed given by the speed limit, especially in urban areas, and the acceleration and deceleration is given by the motor. So it's both of those have pretty low variance. They're pretty uniform across road users. Okay, let's look at pedestrians. So they're on the other side of the spectrum. Their direction, any direction, really multi-directional. They can also change on a dime. It doesn't take them very long to slow down, stop, and then go the other way. Contact is not a great thing, maybe, but it's not a problem. If there's a very dense pedestrian flow, it's not going to be a problem if they bump up against each other or touch shoulders and then keep going. The interactions are not regulated at all. They're just happen based on being human. You look at someone, you maybe try to decide who's going to go which way. It's culturally influenced, but it's not planned. Speed and acceleration and deceleration, they are determined by the physical capability. So this is the same for all active mobilities, that it's a human machine. It's human power that's going into the legs or well, normally the legs, maybe the arms, to make the person move. And as people are very different, there's a huge variation on how fast they walk and how fast they accelerate and decelerate. And of course, my dear bicycles are somewhere in the middle of this. As a cyclist, you can behave a lot like a vehicle if you want to, that you travel in one direction, try not to hit people. In general, it's not great to hit people on a bicycle, but maybe not as bad as a car. Your interactions, it depends on how you ride your bicycle. If you follow the traffic rules or not, they tend to be more flexible road users that don't always stick to the rules. And again, the speed is very different. Okay, but what about all of these road users? Please excuse my funny collage that I made, but I tried to pick out some of the new things that are coming or already here to see what we know about them. This is a Twizy. It's a tiny little car that you see sometimes driving around. And the thing that I like about this picture is this car looks very much like this bike, which is a new e-bike that was developed from a European project. It has an air filter, so inside of this little pod, you only breathe clean air and you can sit comfortably, and there's mirrors and you have a nice motor to help you go through. So, I mean, these things are getting pretty close to one another. Bicycles are also not the same shape or not as uniformly shaped as they used to be. This right here is the type of bicycle that I want to get. A very strong motor to make it up the hills in Wuppertal, but there's also this shape or e-scooters. There's many different types of vehicles on the road now. And what do we know about them? What do we know about their dynamics? How do they drive? And what about their behavior? Where are they on this spectrum? Are they more like motor vehicles or are they more like pedestrians? Are they more free or less free? What do they do? Okay, so let's look at the simulation paradigms, like I call them for this presentation that we have. We only have 2 of them, so it won't take too long. The first that we have is unidirectional traffic. So we have this one that's been existing for a while, where, well, normally used to just be cars, but now sometimes bicycles or other things, they travel along a road segment in one direction with a 1D vector. So they have a position on that road, but it's only one-dimensional, and they just follow each other. So the most important model that we have, behavior model, is this model that describes how they follow. So a car following behavior model, which can be applied to a cyclist. Not very realistically if you have just this basic car following model. If lateral behavior wants to be, or if you want to simulate it, it's done using discrete choice. So the car can either be on the left-hand lane or the right-hand lane, or one of the 3. If there's more lanes, then they choose between them. And they move in some sort of smooth way to this new or other lane. If you want to extend this a little bit, the same idea exists here, the sublane approach that's taken in Zumo and also some other simulation softwares, that you keep this idea that you have continuous longitudinal space, a 1D road that they follow along it, but you divide it up into more lanes. So this discrete lateral space selection is more free, that the cyclist can choose to ride more on the right-hand side, and the vehicles can pass a little bit to the left, but in the same lane. So this is an extension, but it's still the same basic idea, but it lets us simulate traffic or urban traffic a little bit more realistically. Okay, the second one that we have, oh, sorry, I just realized that I didn't change this to a number 2, but this is the second one. And the second one that we have is continuous 2D space. So this is used often for pedestrians, that they can pick anywhere that they want to go. There's no lanes, there's no one-dimensional path that's leading them anywhere. They just select where they want to go. And usually the models that we have here are force models. And those work by detecting any other people, pedestrians, any other obstacles that are in this 2D space. giving our pedestrian a goal or number of goals, sub-goals, or interim goals, that they avoid the obstacles and follow their goals and find their own way through this two-dimensional space. So what can we simulate for pedestrians? Sidewalks, we can do. It's okay. We can either say that our pedestrians are sort of like vehicles and they go in one direction, and maybe they have some lateral flexibility with some sublanes, but and they walk maybe in both directions instead of one direction. Or we make it more complicated and say these sidewalks are open to the spaces, continuous spaces, that they can be led with some sort of force model. And these pedestrian zones, so if there's just pedestrians, that's also no problem. We can use our social force model or whatever model it is for pedestrians, and they can interact with each other and find their way to their goals. And this is also no problem. Also, when these two types of paradigms meet, we can also deal with it. We can say when there's a pedestrian crosswalk here, for example, crossing a road, we can control the interaction using time gaps or space gaps and say they have to give this certain amount of space between different road users. We can assign right of way. We can make sure that the vehicles only go when the sidewalk is not blocked. And this can be done with, of course, sidewalks or without sidewalks. This is okay. There are solutions for doing that too. But what is difficult with simulation is this type of situation. So we have pedestrians that are walking in their two-dimensional space like they do. And we have some cyclists who seem to be mostly going across this way. So it's a little bit more complicated. And we don't know which paradigm is the one we should use. Is this mostly open 2D kind of space, or is this maybe somehow a directional space? And if so, how do we simulate these interactions? They're definitely more complex than just giving right of way and calculating a time gap. There's something going on there that is difficult to get into the simulation. So this is our mixed traffic idea or a situation that is hard to simulate. Okay, let's see how long I've been talking now. Now I want to go away from my arguing for bicycle traffic and active mobility and look at what we're doing when we're improving the situation, and think about how we make sure that we're improving the situation in a good way. So I started working a year ago at my new professorship, bicycle traffic, and I told everyone my research focuses, like I just told all of you, modeling, simulation, data, and everyone said, oh yes, that's very nice and very interesting, but tell me, what can my city do to improve the situation for cyclists? What kind of infrastructure do we need? And they all asked, of course, how wide should a bicycle lane be? The optimal one. What about communication and transformation? What do we need to know about that? How about the guidelines? Oh, in all honesty, I'm just not a guideline person, but there are a lot of really important guidelines in Germany that we need to follow to design infrastructure for our cities. What use is my work in simulation for these guidelines? I can't see my thing here. What about equity? What do we have to think about different people and their access to e-bikes, for example, here in Wuppertal? And the one that I also get a lot, why is this transportation turnaround not happening? I missed the word. Why is it not happening? What are we missing? What's the thing that that is stopping us from getting a new transportation system? So then I've been thinking a lot in this year how I can bring these two worlds together. This simulation world, microscopic modeling, behavior models, different data sources, bringing it into the simulation, improving that with what people actually want to know from a person who's specializing in traffic, but is maybe not in the same world. And thinking about how I and we or everybody can reconcile these two different things. So the first thing that I want to say is to ask the right questions when you're doing a simulation experiment. I brought one example with me. It's not from a simulation study that I did. It's a data analysis study, but still I want to tell this small story just to make the point. I was working with the city of Munich to test out these green signal countdown displays. So these little numbers here tell you how many more seconds that you have until the light is going to turn red. And the city of Munich was really excited to try these out. which was very nice. They are excited to try a lot of different things out for the bicycle traffic. But it was really important that there wasn't a lot more red light running behavior. That's what they didn't want. So I collected data before they installed these signal displays. And what I looked at is the red light running behavior of those people who were just at the stop line or before the stop line when the signal turned red. So these guys here, these are the ones, they were 10 meters or less between the stop line and further along when the light turned red. And as you can see, most of them ran the red light, which isn't surprising because there's this time you can't really stop, or it's not worth it to stop, or you think, oh, I'm faster than everybody else. I can make it in the safety time that's between the signals, and they go. So that wasn't very surprising. And what was good to see is that for people further and further and further away from the stop line, they were more likely to stop. So the people more than 40 meters away were quite likely to stop and wait until the light turned green again and then go. So we didn't see too much red light running behavior for the cyclists, at least if they were far enough away from the signal that, that they could reasonably stop. So then the city of Munich installed this countdown signal display, and then I collected the data again. And then I saw, okay, in this after scenario, there's a lot more red. Uh-oh. So these people now, 0 to 10 meters, they are definitely running the signal. All of these categories here until the over 40, they got more red, which meant there were much more people, many more people running the red signal after these signal displays were installed than before. So that was not good news. It was not good news for the city of Munich, and it was not very good news for me because I was really excited to have these countdown displays there. And I took this, oops, sorry, I didn't want to show you yet. I took this data and these findings to the Cycling Research Board conference in Delft. And I presented them and I said, everybody, maybe it's not a good idea. Maybe we should not have these countdown signal displays. They're leading to red light running behavior. And there, I did not get the same response that I did in Munich or at my chair of traffic engineering control. People said, you are blaming the victim. And then they showed me this picture. They said, Heather, what do you see in this picture? And I said, oh, well, here I see a deer and it's crossing a road and it looks like I might even be in a car. So it's a little bit dangerous that I might hit this deer. So this is a deer crossing the road. And they said, yeah, like that's a very good analysis on a very surface level. Congratulations. But if you look a bit deeper, maybe this is not a deer on the road. Maybe this is a road crossing the forest. Maybe this deer is going along his business as per usual or as he should do. And this road where I'm on with my car is actually disturbing him or putting him in danger, or her. I guess it's her, actually, this deer. So maybe if you think about it, traffic signals, they're a relic from a motorized city. They are there so that cars don't run over other road users. And if we were only cyclists and only pedestrians, we could most likely interact with each other. We're at a slow enough speed that we could find pathways along or across each other, and we wouldn't need to have a traffic signal. And furthermore, with this traffic signal that we do have now in most cities, is it a problem that bicyclists are not obeying them? Is it dangerous? The person asked me there. And of course, at the time I said, yes, it is a problem. It's not good. We don't want bicyclists riding over red signals. But then they asked, did you observe any really critical situations? And I said, well, no, but my data, I didn't collect it for so long. Any indication that there was a safety problem? And then I had to say, no indication of that, especially when they turn right, which is very often, there's no problem at all. The bicycle just stops, makes sure the situation is safe, and then continues on. And that really got me thinking. I was really happy that that person called me out, although it was embarrassing at the time, to think a little bit more about the research question I had. Did it make sense to hold bicyclists to the same rules as car drivers are? Okay, my next point that I want to make is working smarter, which I don't think I have to argue at all in this group of people. People want to automate things and make importing data and roadmaps easier and better. This is a task map or a schedule or a suggested schedule for simulation studies. So in the American guidelines for applying traffic microsimulation modeling software. And then they say, okay, you should define your scope, then collect some data, then build your model and check it. And then you have to spend this big long time here calibrating it. So this is a picture that a good friend of mine sent me when I was still in Munich, and she said, this is an example you have to work for a good fit. If you just fake it, your model is not going to be good. It's going to be a bad model. And of course, you're not going to get good results from any of the alternative analyses that you're going to do afterwards. But calibration is actually a minimization problem. We have a number of parameters that we can change between some certain values, and we want to change these parameters together so that we get the lowest difference or the smallest difference between what we have observed in our data and what our model is telling us. So could be that it is hard work. You still have to get fit. You have to be in shape. Your model has to fit the reality, but maybe a machine can do a lot of the heavy lifting for us. This is just one example. Of course, there's many ways that simulation can be automated, or that we can use different things to take the workload off the people's shoulders, which of course takes the probability for human mistakes out of the simulation task and make everything more manageable. Okay, share what you do. This is probably also something, luckily, that I don't have to argue here. It's my favorite thing about, no, it's hard to say my favorite thing about Sumo, but one of my favorite things is that it's an open source simulation software that you can just use openly and freely without paying for it. But of course, the first thing is data. And this, since I moved to Germany, has improved like 200%, no, more than that. I don't know. It's way better. When I first got here, there was almost no open data. And now a lot of people are moving more in the direction. You can look at almost any city online and find their at least some traffic count data. But also when you're a researcher and collect something, I, for example, collected video data and then tried to take the trajectories out of it for different road users. This type of data, we should share with other people as much as possible. The code that you have, this is something that I'm working on because I am I'm not a programmer. I'm a person who tries to program or uses Python to do some tasks, and I'm always very embarrassed or unsure of how that code looks because it's really definitely not the right way to do anything. It just works in an ugly way. But I'm trying to get as many of these things online so that other people can use them. Let's save time for other people with making things available, no matter how ugly it might look, or maybe you try to clean it up and then share it. And another point is publishing. One problem in Germany that we have is that a lot of universities don't give access to Elsevier anymore, and rightly so. They're asking for a lot of money for work that has been done by researchers that are already paid by that university or by the Bundesland that they're working in. So we can't get it. So why do we publish there anymore? If you can, and if you have something to publish, please think about how other people in the community are going to get it. Are they going to be able to just log on with their university login and download it, or is it going to be difficult? Do you have some money, or does your institution have some resources for publishing open access? And if it does, is it possible for you to make use of it? And if it can, then I suggest you do it. In very least, preprints and ResearchGate. If somebody asks you for your research, then it would be very nice to give it to them. Okay, making findings and tools usable. A lot of the time when we're working on something, we get so deep into it that it seems obvious, or it seems like the results that we get are self-explanatory. People just need to look at the chart and then they get it. But it's often not like that. I remember I was working, programming in my bad way that I do. And finally something worked, and I would get so happy about it and send this result that was working to a colleague. And they would say like, whoa, you seem really happy about it. By looking at these numbers or this screenshot, I cannot understand anything. And this also relates back to the people who come to me and say, Heather, great that you model and simulate, but what should I do for my city? We need to make sure that we take this extra step after everything's done to make everything understandable and usable and nice to look at, add some nice diagrams that explain the results as best as we can. And the final point that I want to make, this list, I had to cut it short at some point because I was just having too long of a list, but something that we need to do is educate future experts for this new transportation turnaround that we're having. So they need to have a whole wide variety of skills, so programming and software, but urban design and planning, a lot of sociology. What mobility is a sociological question, and our transport system is just trying to meet these mobility needs. So we really need to talk to the sociologists and hear their opinions too. Traffic engineering is a term that in some circles has gotten very unpopular, but we need somebody to engineer our road network or our city mobility network, and this is a traffic engineer, and that's what I am. So I hope it's still a necessary skill to have also in the future. Technologies, so not only bicycle technologies, but in my case, yes, but technology in general. How should vehicles in the broadest sense of the word look in the future? Psychology, how do people perceive and see things? How do they act on when they're using different modes? What's important to consider there? And different things like transition management and communication and sales and storytelling. Storytelling is a incredibly important thing because you can spin reality. Everybody knows this. It's a huge problem in our world. You can spin reality in so many different ways. And sometimes it's just the person with the best story or the most interesting story that makes you follow their way. So maybe we need to focus on learning how to tell stories a little bit better. Okay, but political science, of course, also very important. A lot of people wish that I was a politician, and maybe not because I'm good at it, but because they ask for recommendations from a political perspective about how to improve the bicycle situation, which unfortunately I don't know. Okay, but what I do know is that I'm planning a new master's program. It's part of the Stiftungsprofessor that there will be many new master's programs. What our program is an international program, which is a little bit different than the other ones. I have the feeling, or not for me and for people, I just learned so much from the different cities that I visited. They're all so different. They all have different conditions and different problems and different solutions that would work or not work. That I think it's important when anyone's studying transportation to see some different things, some different options, some different approaches, some different people who think in a different way. It's just important to get a full and open picture of things. So anyways, in this program that's coming, the students will spend a semester first in Amsterdam, where of course you can see a wonderful situation for cycling. Then they will come to Wuppertal and see a different situation, a city that's at the beginning with a lot of challenges, but people that are willing to face those challenges head on. And then the last semester will be in Lund in Sweden at the University of Lund, where, as we might know, there's a lot of expertise about traffic safety and how we can head for Vision Zero where there's no accidents. So that is the concept of the Cycling Futures Master's Program that's coming. It's being built up, but it will take a little while, maybe next year, maybe the year after. Let's see when it's actually going to come and when we're going to search for students. But keep it in mind if you know anybody who's wanting to study in a few years at the master's level. Okay, that was my presentation for today. My presentation took a little bit of a different life than I had planned in my abstract, but I hope it was nevertheless interesting for you. Anybody who wants to or is interested, please get in touch with us. We're very interested to hear about other people's perspectives and work and anything they're doing with data or simulation. I put my email address there. Our website is a little bit under construction. We're just shifting away from a very old, terrible website to a new one that's not so terrible, but not quite done yet. So if you go there, just be a little bit patient. All right, great. Then I'm very happy to answer any questions or discuss anything that you might like.